In this lecture, we'll delve into the concept of generating functions and Gaussian random vectors. First, let's set the stage. Consider a continuous random variable x, which maps outcomes from our sample space omega onto the real line. This variable exists within a probability space defined by omega, the sigma field script f, and the probability measure p. Associated with x is its distribution function f sub x, which maps the real numbers to the interval 0 to 1. Now let's introduce the first type, the characteristic function. Imagine we define j as the imaginary unit, that's the square root of -1. We can then demonstrate that a function h sub mapping from the reals to the complex numbers, defined as h sub u of x, is e to the power jux, which using Euler's formula is cosine of ux plus j times sine of ux. This function is Borel measurable for any real number u. This implies that when we apply this function to our random variable x, the result h sub u of x mapping omega to the complex numbers is itself a complex valued random variable within our probability space. With that established, we can formally define the characteristic function. For a random variable x mapping omega to the reals defined on our probability space omega script f p, its characteristic function denoted phi sub x maps the real numbers to the complex numbers. It's defined as phi sub x of u is the expectation of e to the power jux for all real u, remembering that j squared equals -1. An important reminder about the characteristic function phi sub x of u. It is always finite. Why? Because the magnitude or absolute value of phi sub x of u, which is the magnitude of the expectation of e to the jux, is less than or equal to the expectation of the magnitude of e to the jux. Since the magnitude of e to the jux is always 1, its expectation is also 1. Thus, the magnitude of phi sub x of u is bounded by 1. Just to recap how this applies in different scenarios. For a discrete random variable, x taking values in a set script, x with a probability mass function p sub x, the characteristic function phi sub x of u is calculated as the sum over all x in script x of e to the power jux times the probability p sub x of x. And for a continuous random variable x mapping omega to the reals with a probability density function f sub x, the characteristic function phi sub x of u is found by integrating from minus infinity to infinity the term e to the power jux times the density f sub x of x with respect to x. Let's look at a key example, the Gaussian random variable. If x is Gaussian with mean and mu and variance per sigma squared, its characteristic function phi sub x of u is given by the expression 1 over the square root of 2 pi sigma squared times the integral over all real x of e to the jux times e to the power minus fraction x minus mu squared over 2 sigma squared dx, and this integral evaluates to the exponential of the quantity minus u squared sigma squared over 2 plus ju mu. An interesting observation here is that the magnitude of this characteristic function, the absolute value of phi sub x of u, which is e to the power minus u squared sigma squared over 2, exhibits Gaussian decay centered at 0 with a variance of 1 over sigma squared. Now let's consider the relationship between moments and the characteristic function. A crucial theorem states that if the expectation of the absolute value of x raised to the power n is finite for some positive integer n, then the kth derivative of the characteristic function, let's write it as phi sub x superscript k of u, exists, is finite, and is a continuous function of u for all k up to n. Furthermore, evaluating this kth derivative at u equals 0 gives us phi sub x superscript k evaluated at 0 equals j to the power k times the kth moment of x, which is the expectation of x to the k for all k up to n. The proof relies on the fact that if the expectation of absolute x to the n is finite, then the expectation of absolute x to the k must also be finite for all k less than or equal to n. This ensures the existence and finiteness of the moments, the expectation of x to the k. We can justify interchanging the order of differentiation and expectation, essentially differentiating under the integral sign, because e to the jux is a bounded function with bounded derivatives. Performing this differentiation k times with respect to u and then setting u equals 0 yields phi sub x superscript k evaluated at 0 equals the expectation of the kth derivative of e to the jux with respect to u evaluated at u equals 0, which simplifies precisely to j to the k times the expectation of x to the k. Another fundamental theorem, though we won't prove the sufficiency part here as it's quite involved, states that two random variables possess the same probability distribution if and only if they have the same characteristic function. The necessity that the same distribution implies the same characteristic function is relatively straightforward to see from the definition. Moving on to section 1.2, let's discuss the moment generating function, or MGF. Consider a function g sub t mapping reals to non-negative reals, defined as g sub t of x equals e to the power tx. Since the exponential function is monotonic, g sub t is Borel measurable for any real number t. Consequently, applying this function to our random variable x, the result g sub t of x mapping omega to the non-negative reals is a positive random variable within our probability space. This leads us to the definition of the moment generating function. For a random variable x on our probability space, the MGF, denoted m sub x, maps the real numbers to the non-negative reals. It's defined as m sub x of t equals the expectation of e to the power tx for all real values of t for which this expectation is finite. It's important to remember that while the characteristic function always exists, though it might be complex, the moment generating function might not exist or be finite for all t. However, when the MGF does exist, it can sometimes be simpler to work with, especially since it's real valued. A useful lemma connects the MGF to the moments of x. If the MGF m sub x of t is finite for some t, then it can be expressed as a power series m sub x of t equals 1 plus the sum over all positive integers n of t to the power n over n factorial times the nth moment, the expectation of x to the n. The proof starts with the Taylor series expansion of e to the theta around 0, which is e to the theta equals 1 plus the sum from n equals 1 to infinity of theta to the n over n factorial. Now substitute theta equals t times x. This gives us e to the power t x equals 1 plus the sum from n equals 1 to infinity of t to the n over n factorial times x to the n. Taking the expectation on both sides and assuming we can interchange expectation and summation, which holds if the expectation is finite, the linearity of expectation yields the result m sub x of t equals the expectation of e to the tx equals 1 plus the sum from n equals 1 to infinity of t to the n over n factorial times the expectation of x to the. Let's revisit our Gaussian example. For a Gaussian random variable x with mean mu and variance sigma squared, the moment generating function m sub x of t is given by the exponential of the quantity t squared sigma squared over 2 plus tmu. Now for section 1.3, the probability generating function PGF. This is particularly useful when dealing with non-negative integer valued random variables, say x mapping omega to a subset script x of the non-negative integers z plus. The PGF is essentially the z transform of the probability mass function. Formally, for a discrete non-negative integer valued random variable x with PMF p sub x, the probability generating function psi sub x maps complex numbers to complex numbers. It's defined as c sub x of z equals the expectation of z raised to the power x. This can be calculated as the sum over all x in the support script x of z to the x times the probability p sub x of x. This definition holds for complex numbers z, where the magnitude absolute z is less than or equal to 1. A useful lemma states that for a non-negative simple random variable x, the magnitude of its PGF, absolute phi c sub x of z, is always less than or equal to 1 whenever the magnitude absolute z is less than or equal to 1. The proof is quite direct. Let z be a complex number with magnitude at most 1 and let p sub x be the PMF of x. Since x takes only non-negative values x, we can write the magnitude absolute psi sub x of z as the magnitude of the sum over x in script x of z to the x times p sub x of x. By the triangle inequality, this is less than or equal to the sum over x in script x of the magnitude of z to the x times p sub x of x, which equals the sum over x in script x of absolute z to the power x times p sub x of x, since absolute z is less than or equal to 1 and x is non-negative, absolute z to the x is less than or equal to 1. Therefore, the sum is bounded above by the sum over x in script x of p sub x of x, which is simply the sum of all probabilities equaling 1. Now let's connect the PGF to factorial moments. A theorem states that for a non-negative simple random variable x, whose kth moment expectation of x to the k is finite, the kth derivative of its PGF evaluated at z equals 1 gives the kth order factorial moment of x, that is psi sub x superscript k evaluated at 1 equals the expectation of the product x times x minus 1 times x minus 2 down to x minus k plus 1, or the expectation of the product from I equals 0 to k minus 1 of x minus I. The proof follows from interchanging differentiation and expectation or summation in the discrete case, which is generally permissible here. As a reminder, we can recover the regular moments from these factorial moments. For instance, the first moment, expectation of x, is simply the first derivative psi sub x prime evaluated at 1. The second moment, expectation of x squared, can be found from the second factorial moment, which is the expectation of x times x minus 1 or psi sub x double prime evaluated at 1. Specifically, the expectation of x squared is psi sub x double prime at 1 plus psi sub x prime at 1. Similar to the characteristic function, there's a uniqueness theorem for PGFs. Two non-negative integer valued random variables have the same probability distribution if and only if their Z transforms PGFs are equal. Again, the necessity is clear. For sufficiency, observe that the kth derivative psi sub x superscript k of z involves terms like z to the power x minus k. Evaluating this at z equals 0, only the term where x equals k potentially survives, yielding psi sub x superscript k evaluated at 0 equals k factorial times p sub x of k. This shows how the PGF uniquely determines the probabilities p sub x of k for all k. Further justification for interchanging the derivative and summation relies on arguments like the dominated convergence theorem, ensuring the result holds. All right, let's transition to section 2, Gaussian random vectors. Just as we defined the characteristic function for a scalar random variable, we can define it for a random vector x mapping omega to Rn. The characteristic function phi sub x maps Rn to the complex numbers C and is defined as phi sub x of u equals the expectation of E raised to the power j times the inner product of u and x, for u also a vector in Rn. An important property to remember: if the components of the random vector x are independent, meaning x is an independent random vector, then its characteristic function is simply the product of the characteristic functions of its components. That is phi sub x of U equals the product from I equals 1 to n of phi sub xi of ui for all u equals u1 through un in Rn. Now let's formally define Gaussian random vectors. A Gaussian random vector is a continuous random vector x mapping omega to Rn, characterized by its probability density function f sub x of x. This density is given by f sub x of x equals 1 over the square root of 2 pi to the n times the determinant of sigma, all multiplied by the exponential of minus 1/2 times x minus mu transpose times sigma inverse times x minus mu. This holds for all x in Rn. Here, mu is the mean vector in Rn and sigma is the covariance matrix, which must be a positive definite n by n matrix. As a specific example, consider a Gaussian random vector where the mean vector mu has all components equal to some scalar mu1 and the covariance matrix. Sigma is sigma squared times the identity matrix I for some positive scalar sigma squared. In this case, the density simplifies to f sub x of x equals 1 over 2 pi sigma squared to the power n over 2 times the exponential of minus 1/2 times the sum from I equals 1 to n of fraction xi minus mu1 squared over sigma squared. It follows directly from this form of the density that x is an IID, independent and identically distributed random vector. Each component xi is itself a Gaussian random variable with mean mu1 and variance per sigma squared. The characteristic function phi sub x of u for such an IID Gaussian vector is the product from I equals 1 to n of phi sub xi of ui, which evaluates to the exponential of minus sigma squared over 2 times the sum of ui squared plus j mu 1 times the sum of ui. Let's consider a useful lemma. Suppose we have an IID standard Gaussian vector z mapping omega to Rn, meaning zero mean, unit variance components. Let alpha be a vector in Rn and mu be a scalar. Then the affine combination y defined as mu plus the inner product of alpha and z is itself a Gaussian random variable. Let's outline the proof. First, find the mean of y by linearity of expectation, and since z is zero mean, the expectation of y is simply mu. Next, let's find the variance. Let's call it sigma squared, the variance of y. This is the expectation of y minus mu squared. Since y minus mu is the inner product of alpha and z, or the sum of alpha I z I, the variance is the expectation of the square of this sum, which is the expectation of the double sum over I and k of alpha I alpha kz I z k. Using linearity, this is the double sum of alpha I alpha k times the expectation of z I z k. Because the components zi are IID standard Gaussian, the expectation of zi z k is 1 if I equals k and 0 otherwise. This simplifies the double summation to the sum over a of alpha I squared, which is the squared L2 norm of alpha, or simply the inner product of alpha with itself. So the variance sigma squared is the sum of alpha I squared. To confirm y is Gaussian, we need to show its characteristic function has the Gaussian form. We aim to show phi sub y of u equals the exponential of minus u squared sigma squared over 2 plus ju mu for any real u. Recall that since Z is an IID standard Gaussian vector, each component Zi has the characteristic function phi sub Zi of V equals the exponential of minus V squared over 2. Now, compute phi sub y of, which is the expectation of e to the juy, substituting y equals mu plus the sum of alpha izi, we get the expectation of e to the power ju times the quantity mu plus sum alpha izi. This equals e to the ju mu times the expectation of e to the power j times the sum of u alpha izi. Because the zi are independent, the expectation of the product is the product of expectations e to the ju mu times the product from I equals 1 to n of the expectation of e to the ju alpha izi. Recognizing the expectation term as phi sub z evaluated at u alpha I, this becomes e to the ju mu times the product from I equals 1 to n of phi sub zi of u alpha I. Substituting the standard Gaussian characteristic function, we get e to the ju mu times the product from I equals 1 to n of the exponential of minus u alpha I squared over 2. This simplifies to e to the ju mu times the exponential of minus u squared over 2 times the sum from I equals 1 to n of alpha I squared. Since sigma squared is the sum of alpha I squared, this simplifies to the exponential of minus u squared sigma squared over 2 plus ju mu, which is exactly the characteristic function of a Gaussian random variable with mean mu and variance sigma squared. This leads us to a fundamental theorem characterizing Gaussian random vectors. A random vector x mapping omega to Rn is Gaussian with parameters mu and sigma if and only if the vector z defined as sigma to the minus 1/2 times x minus mu is an IID standard Gaussian random vector. Here sigma to the 1/2 represents a matrix square root of sigma. Let's sketch the proof. First, assume x equals mu plus sigma to the 1/2 times z, where z is an IID standard Gaussian vector. We want to show x has the Gaussian density using the transformation of random vector densities. The transformation is x equals g of z equals mu plus sigma to the 1/2 z. We need the Jacobian determinant. Let's consider the inverse transformation. Z equals sigma to the minus 1/2 times x minus mu. The Jacobian matrix of z with respect to x is sigma to the minus 1/2. Its determinant is the determinant of sigma to the power minus 1/2. The transformation rule is f sub x of x equals f sub z evaluated at z of x times the absolute value of the determinant of the Jacobian of z with respect to x. The density of the standard Gaussian vector z is f sub z of z equals 2 pi to the minus n over 2 times the exponential of minus 1/2 z transpose z. Substituting z equals sigma to the minus 1/2 times x minus mu and multiplying by the absolute determinant, which is determinant of sigma to the minus 1/2, we get f sub x of x equals 2 pi to the minus n over 2 times the exponential of minus 1/2 times the quantity, sigma to the minus 1/2 times x minus mu transposed times sigma to the minus 1/2 times x minus mu, all multiplied by determinant of sigma to the minus 1/2. Assuming sigma is symmetric, the term in the exponential simplifies to minus 1/2 times x minus mu transpose times sigma inverse times x minus mu. Combining the constant terms gives 1 over square root of 2 pi to the n times determinant of sigma. This yields exactly the definition of the Gaussian density for x with parameters mu and sigma. Conversely, if x is a Gaussian random vector with the standard density, we can perform the transformation z equals sigma to the minus 1/2 times x minus mu and show, using the transformation of densities again, that z has the standard normal density, confirming it's an IID standard Gaussian vector. So to reiterate this important equivalence, a random vector x with mean mu and covariance, sigma is Gaussian if and only if it can be represented as x equals mu plus sigma to the 1/2 times z, where z is an IID standard Gaussian vector. From this representation x equals mu plus sigma to the 1/2 z, it follows directly that the expectation of x is mu. Since the expectation of z is 0, also the covariance matrix, the expectation of x minus mu times x minus mu transpose becomes the expectation of sigma to the 1/2 z times z transpose sigma to the 1/2 transpose. Assuming symmetry and knowing the expectation of z transpose is the identity matrix, this simplifies to sigma to the 1/2 times I times sigma to the 1/2, which equals sigma. Now let's observe the components of the Gaussian vector x equals mu plus az, where we use a for sigma to the 1/2. Each component xi is given by xi equals mui plus the sum from k equals 1 to n of a I k z k. As we established earlier, this is an affine combination of IID standard Gaussian variables zk. Therefore, each component xi is itself a Gaussian random variable. Its mean is mu I. Its variance is the sum from k equals 1 to n of a I k squared. This sum is precisely the ith diagonal element of the matrix A transpose. Since A transpose equals sigma, the variance of xi is sigma ii, the ith diagonal element of the covariance matrix sigma. Finally, let's compute the characteristic function phi sub x of u for a general Gaussian vector x equals mu plus az using the known distribution of z. We have phi sub x of u is the expectation of e to the j inner product ux. Substituting x, we get the expectation of the exponential of j inner product u with mu plus az. This expands to the expectation of exponential of j inner product mu plus j inner product u with az. Using the transpose property for the inner product, inner product u with az equals inner product A transpose u with z. So phi sub x of u equals exponential j inner product u mu times the expectation of exponential j inner product A transpose u with z. The expectation term is the characteristic function of z evaluated at the vector A transpose u. Recall phi sub z of v is exponential minus 1/2 norm v squared or exponential minus 1/2 v transpose v. So phi sub z of A transpose u is exponential minus 1/2 times A transpose u transpose times A transpose u, which simplifies to exponential minus 1/2 u transpose AA transpose u. Since AA transpose is sigma, this is exponential minus 1/2 u transpose sigma u. Putting it all together, phi sub x of u equals exponential of the quantity jj inner product u mu minus 1/2 u transpose sigma u. This is the characteristic function for a Gaussian random vector with mean mu and covariance sigma. An important consequence arises for Gaussian vectors. If the components are uncorrelated, they are also independent. The proof is straightforward. If the components of a Gaussian vector x are uncorrelated, its covariance matrix sigma must be diagonal. Let sigma be the diagonal matrix with diagonal entries sigma 1 squared through sigma n squared. Then sigma inverse is diagonal with entries 1 over sigma I squared, and the determinant of sigma is the product of sigma I squared. The quadratic term in the exponent of the density function becomes minus 1/2 times the sum from I equals 1 to n of xi minus mu I squared over sigma I squared. The density function f sub x of x then becomes 1 over the square root of 2 pi to the n times the product of sigma I squared times the exponential of this sum. This expression separates into a product from I equals 1 to n of the individual Gaussian densities 1 over square root 2 pi sigma squared times exponential minus xi minus mu I squared over 2 sigma I squared. Each term is the density f sub xi of xi for a Gaussian variable xi with mean mui and variance sigma I squared. Therefore, f sub x of x equals the product from I equals 1 to n of f sub xi of xi, which confirms the independence of the components xi. With this, we conclude the lecture.